Welcome to the new era of video creation with BOZ8. Today, we will discuss implement retrieval-augmented generation, RAG, in a large language model. Question: how would you implement retrieval-augmented generation, RAG, in a large language model to improve factual accuracy and reduce hallucinations? Retrieval-augmented generation, RAG, is a framework designed to enhance large language models by integrating real-time document retrieval. The traditional method of generating text using pre-trained models may often lead to hallucinations where the model invents information. RAG mitigates this by augmenting the model's responses with external factual data at inference time. The retrieval system uses external knowledge sources such as vector databases, search engines, or structured knowledge bases to find relevant information that can be used by the model to generate accurate, fact-based responses. This approach is particularly useful for applications like chatbots and enterprise AI solutions, where precise information is critical. The RAG system consists of two main components, the retriever and the generator. The retriever is responsible for searching through a large knowledge base to find the most relevant documents based on the query. Once documents are retrieved, the generator integrates them into the response. A critical aspect of RAG is the embedding model. This model converts text into vector representations, enabling fast and efficient document retrieval. The indexing and storage layer is responsible for organizing these documents in vector databases, such as FASS or Pinecone, ensuring that retrieval happens with low latency. There are several strategies for document retrieval in a RAG system. Sparse retrieval methods such as BM25 and TF-IDF are keyword-based and work well for simple tasks, where exact matches are sufficient. These methods are efficient but may lack semantic understanding. Dense retrieval, on the other hand, uses machine learning models to generate vector embeddings for documents and queries. Models like DPR, dense passage retrieval, and BERT are used to enhance semantic matching, ensuring that documents are not just matched by keywords, but by meaning. A hybrid retrieval approach combines the strengths of both sparse and dense retrieval methods. By using sparse retrieval to narrow down the document set and dense retrieval for ranking, we can achieve better overall performance. Multi-hop retrieval is also important for answering more complex questions that require information from multiple documents or knowledge sources. Optimizing the generator is crucial for ensuring that retrieved information is incorporated effectively into the response. Fine-tuning the model on domain-specific data can improve its ability to process context, but prompt engineering is a more cost-effective and flexible approach. By carefully designing the prompts, we can direct the model to focus on relevant information. Context management is another challenge, especially when dealing with long documents. LLMs have token limits, so techniques like document chunking and ranked passage selection are essential to ensure that the most relevant context is fed to the model. For fusion techniques, methods like fusion in decoder, FID, which process multiple passages at once, can help generate coherent responses even when multiple documents are involved. Additionally, adaptive confidence scoring allows the model to reject answers that are uncertain or based on unreliable retrieved documents. Scaling a RAG system requires ensuring that both the retrieval and generation processes can handle large volumes of queries efficiently. Sharding vector databases across multiple servers helps distribute the load, improving retrieval speed and reducing the risk of bottlenecks. To reduce latency for frequently queried topics, caching can be used to store the results of previous retrievals, so they don't have to be recomputed. Pre-retrieval techniques allow the system to store useful documents ahead of time, further improving response times. Asynchronous execution enables parallel execution of retrieval and generation, which helps improve throughput and responsiveness. When considering deployment, it's important to weigh the benefits of edge versus cloud deployment. Edge deployment offers faster response times, but may have limited resources, while the cloud provides better scalability, but at the cost of latency. Even with the addition of a retrieval system, hallucinations can still occur when the model generates content not supported by the retrieved documents. One way to address this is by using self-consistency methods. This approach involves generating multiple responses to a question and selecting the answer that is most consistent across the different generations. Another effective strategy is retrieval confidence filtering, where we use the confidence score of the retrieval system to decide whether the generated response is trustworthy. If the confidence score is low, the model may generate hallucinated or unreliable information. Knowledge verification models can cross-check the output against trusted sources like Wikipedia, academic papers, or custom knowledge databases. Finally, for high-risk or critical applications, human-in-the-loop systems can be employed to involve experts in the decision-making process, ensuring accuracy when AI confidence is low. The future of RAG systems is likely to involve multimodal retrieval, where the system can retrieve and generate responses based on a combination of text, images, and videos. This could be useful in a variety of applications, such as medical diagnostics or automated content generation. Federated RAG is another emerging trend, allowing knowledge to be retrieved from decentralized sources while preserving user privacy. Instead of centralizing data, the system can query knowledge stored in multiple locations without needing to transfer sensitive information. The ability to continuously update knowledge bases in real time is a game changer. Continuous learning enables RAG systems to adapt quickly to new information, ensuring that they remain accurate and up to date. Finally, knowledge distillation techniques could be used to create more computationally efficient RAG models, reducing the computational cost associated with running large-scale systems. Evaluating RAG systems requires a multifaceted approach. Precision and recall are key metrics for assessing how relevant the retrieved documents are to the given query. A high precision means the system is returning highly relevant documents, while high recall means the system is retrieving all relevant documents. Response coherence is crucial for assessing how well the generated response integrates the retrieved content. It includes both fluency, how natural the text sounds, and factual consistency, how accurate the response is. Latency and throughput are important when scaling RAG systems. Latency refers to how quickly the system can generate a response, while throughput refers to the number of queries the system can handle per second. Finally, human feedback is invaluable for continuously improving the system based on real-world performance. Despite its advantages, RAG comes with challenges. Knowledge drift refers to the issue of retrieved information becoming outdated or inaccurate, especially when dealing with dynamic fields like news or scientific research. Continuous updates and monitoring are required to keep the knowledge base accurate. Scalability is another challenge, particularly when dealing with massive knowledge bases. Retrieval performance can degrade if the system is not properly scaled. Techniques like sharding, caching, and parallel retrieval help alleviate this. Bias in retrieved documents is an ongoing issue, especially when dealing with large, uncurated data sets. Using diverse and balanced data sources can help mitigate this problem. Additionally, computational costs remain a concern when dealing with large-scale models. Efficient algorithms and knowledge distillation can help reduce the operational burden. To conclude, implementing retrieval-augmented generation RAG in a large language model involves a balance of effective retrieval strategies, optimization of context integration, and confidence scoring. By carefully selecting the right retrieval methods, sparse, dense, or hybrid, we can ensure that the model is working with the most relevant information. Context integration is key, as it allows the model to generate more accurate responses. Confidence scoring helps reduce hallucinations by rejecting uncertain answers, ensuring that the model outputs reliable information. Finally, continuous updates to the retrieval system ensure that the model stays accurate over time, adapting to new information and reducing the likelihood of outdated content affecting performance.